here, you should actually see very specifically the reduction in entropy in both individual layers as a result of essentially inducing this gap in one layer that forces this to up to sort of exponentially suppress additional states to be in one specific state. So this is something that we can also, of course, then look at the time-dependent dynamics of in terms of a practical process for transferring entropy from one layer to the other. So if you want to use it to cool in an experiment, then we have to be able to make a time-dependent ramp and still see the same sort of suppression of the entropy in one layer that we would expect to see thermodynamically. And we also, at zero temperature, in order to see the dynamical disentangling, need to be able to do this sort of adiabatic process in a reasonable time in the experiments. So the first calculations here are zero temperature calculations as a function of system size, and what we see is that the total time here, measured in units of the tunneling timescale in an individual lattice, what we see is that in fact this only takes a few tunneling timescales before the fidelity of the final state here at zero temperature is very close to 1. You should actually see this, this sort of dynamical disentangling on experimentally reasonable timescales for two coupled 1D chains. If you go to non-zero temperature, the question becomes a little bit more tricky, because we go to non-zero temperature, we have then a complicated spectrum of excited states in the ungapped layer. So the question is to what extent this type of process will still work in cases where the dynamics uncouple you between these different excited states in your ungapped layer. So the dynamics here become then more complicated, both to calculate and physically in general. But what we find is that then that the level of suppression depends on somewhat on optimizing the ramp. In particular, one thing you don't want to do here is go into a limit where these particles are very, very strongly interacting, and it becomes difficult to actually thermalize between the two layers during the ramp. If you reduce the interactions, then you find that these particles the atoms thermalize a little bit more easily, which means that you should see a greater reduction of the entropy in the gapped layer, basically because any excitations that you generate in the dynamical process tend to get thermalized, and so this gap that you have for excitations in this layer down here sort of allows you essentially still to transfer, if you like, the extra entropy that you produce in the ramp into this layer without the gap. So at that point, the details of the ramp become important, and again, it's better to have it in a regime where the system can thermalize better. Now, we looked at this in a couple of different senses for fermions. The difficulty that you have if you, for example, wanted to go straight into an antiferromagnet is that you don't immediately have, for the isotropic case, a spin gap in a Fermi-Hubbard model. And you can introduce essentially a gap in two different ways. You could have a spin-dependent lattice that creates a different tunneling for two different spin species. Or the other thing that you could do, which we looked at, is to have, for example, these dimerized lattices where you have essentially different tunneling on odd and even bonds, and this is very similar to the lattices that were created in these experiments by Daniel, who's one of the organizers when he was in Tim and Esslinger's group back in 2013. And what we see again for this case of fermions and the dimerized lattices, we have a gap, and so we have here essentially spin and charge gaps, and as we change the chemical potential to fill up essentially one of the layers starting below unit filling for the system as a whole, we again see that we can load very high fidelity dimers. And again, we can then take this as a starting point, and what we looked at was taking essentially adiabatic ramps starting from these dimers and going over into sort of a fully connected lattice. And the message here is that if you don't have a gap in the final state that you're trying to produce, what you can do is you can find something that is gapped, that is adiabatically connected in a simple way to the final state that you're trying to produce. And then what we normally find for finite size systems of the scale that you have in the laboratory, you can normally ramp adiabatically from your gap state over into your ungapped state in order to produce something based on essentially the finite size gaps that you have in the experiments. Okay, so for the rest of the talk I'd like to move on to something that we've been thinking about in terms of the out of equilibrium dynamics of transport systems with ultracold fermions. And we've sort of been inspired a little bit by developments sort of both in the solid state and in ultracold atoms, and looking sort of cleanly at new geometries that are a little bit different to what people have looked at in the past. So there have been a lot of developments both in sort of solid state systems with superconducting nanowires, or with oxide heterostructure systems like the LAO-STO system in Jeremy Levy's group in Pittsburgh, where they were able to actually use an atomic force microscope tip to change essentially an interface between these two oxide layers from something that's insulating to something that's superconducting in such a way as to essentially draw a transport system with superconducting wires, which you see here in green, and quantum dots, which you see here in the middle. And this is essentially a way to create and program geometries in a similar sort of sense to these beautiful experiments by Tilman Esslinger and John Philippe Rantou. So what I found myself sort of thinking as a quantum optics theorist is that I wonder if there are ways to sort of take the sort of techniques that we would normally use in quantum optics, where we think about, for example, input and output of an optical cavity, sort of between sort of reservoirs that are our external electromagnetic field, and sort of calculate transport of fermions sort of through the channel, where the channel's a bit like our cavity and the reservoirs are a bit like our external fields. And in addition, can we then actually use the nice description that we have for the sorts of Markovian dissipation that we could in principle add to the channel, adding, for example, dephasing through light scattering or through adding noise to the potential, or adding controlled particle loss to the channel. Can we get sort of interesting sort of changes in the dynamics of this transport system that we might be able to model using sort of quantum optics-like techniques in the sense of sort of analytical and numerical treatments? And then could you, of course, see these in cold gas experiments. So what we did is sort of inspired by a lot of sort of older work in sort of input-output theory in quantum optics that was generalized by a number of different people to sort of fermions entering and leaving a trap. We sort of took another step, and we sort of asked what this would actually give us in terms of the sort of conduction properties when you have sort of some reservoir of fermions, which can be electrons in a lead, or it can be trapped ultracold fermions, and you have a quantum dot, which could be a quantum dot in the solid state, but could also equally be an optical potential of the sort that you have in the experiments by Tilman and John Philippe.
Andrew, 5 minutes.
Okay, perfect. Thanks, Randy. 5 minutes including, not including this. 4 minutes.
Including question.
Okay, thank you. So what we have then is we have coupling in terms of single particle tunneling between the leads and the dots. And in the case that you have pairs here, or indeed that you could drive it in an ultracold atomic physics experiment by, for example, dissociation of molecules, in which case you could add sort of additional combinations of here. You have then sort of this possibility of having Cooper pairs coupling into the quantum dot, and we essentially represent this in our calculations the same way as we would represent a laser drive on a cavity, by having essentially a modular transformation that allows us to put this as a driving Hamiltonian for the quantum dot. So a lot of these calculations then were done by François Daminet, who's a postdoc in our group. And what we're able to do is, in different regimes, then extract what we would expect the conduction properties to be, sort of through the quantum dot. Now, many of these things are things that have been looked at for many years. Of course, this is sort of a classic problem with a quantum point contact or with sort of a single dot coupled, for example, to normal leads. And what we know is that in one dimension, you have sort of quantized conductance, which essentially goes up in steps depending on how many different channels you have through which you can transfer sort of particles from one lead sort of across the dot and into sort of empty states available in the other lead. So this is sort of a classic problem, and you can sort of see how the current that passes through the system depends on the bias between the two leads, which changes the number of accessible channels that you have here in through the dot. What we did was we added in then, as has also been done in several cases, the differences you get when you have superconducting leads where you now have a gap. And of course the normal result of this for the standard part of the current is just that you have sort of a translation of where these steps occur by twice the energy gap based on the density of states in the superconducting lead. You have an energy gap and then a spike. You see the spike here associated with the density of states in the superconductor. What's particularly interesting when you have this drive, though, is the possibility to see the subgap current that you get when this bias voltage is smaller than the gap associated with the superconductor. And here we get something that's been discussed in a number of cases in the solid state. It was seen in terms of subgap transport in a beautiful experiment again in Zurich, where this is a peak that we would normally expect for normal single electron tunneling. These peaks down here correspond to a situation where there normally wouldn't be a state available for an electron to come from here to here, but now if you have a Cooper pair that also tunnels, then this loses energy across the junction, this gains energy across the junction, and the combination then conserves energy. So you get essentially co-tunneling of Cooper pairs that are referred to as multiple Andreev reflections that then give rise to these subgap current peaks. So the new thing we wanted to do then was to ask what happens to this in the presence of these dissipative elements that we can easily add in to the atomic physics experiments and that we can add in to our calculations. So we added in then these loss and dephasing channels sort of through the quantum dot and could see the ways in which, in this case, you got sort of, if you had a loss channel here, a drawing of the Cooper pair current essentially out of both leads and into this effective additional channel that you had coming out over here that sort of decreased the overall current through this lead and drew more current out of the higher chemical potential lead. And what we found, though, was that essentially, whether you looked at a single particle current or a Cooper pair current, the particle loss did the same thing. But if you add dephasing to the system, then you can actually really see the difference between the sort of single particle current and current that is induced by these multiple Andreev reflections, which is a coherent process. And so this dissipation that is dephasing due to noise or indeed in atomic physics, sort of light scattering, will actually specifically suppress just this sort of coherent part of the subgap current and might give a really interesting probe in experiments for cases where the current is due specifically to these types of processes. So going forwards, we see sort of new opportunities to try to tackle problems of quantum transport by sort of applying techniques that we'd normally think of in quantum optics, and especially to study sort of the role of noise with sort of dephasing and particle loss on coherent phenomena and more complicated phenomena that you might get as you add in more dots and look at systems of interacting electrons sort of on sort of combinations of dots. We want to know, of course, if also in the solid state, oops, I had some sort of autocorrect thing happened there, I apologize for that. We want to see if we can actually use this maybe to engineer states in a quantum transport setting, especially by asking quantum optics questions like, can we now actually observe the output? Can we observe particles lost through this additional channel? Can we observe particles being transferred into the second reservoir and try to infer sort of what's going on in a state of electrons maybe in a series of dots or atoms in a series of lattice sites between the two reservoirs by making those measurements? Or could we use even quantum feedback to engineer these systems? And for bigger systems, we'd like to combine this with tensor networks and use this to take bigger and bigger systems between the two leads. So with that, I'd like to thank the people who worked on this, especially François Daminet, who did the calculations for the transport part of this, and our various external collaborators who worked on both parts with us. So thank you very much.
So going back to this idea of cooling by what you call dynamical disentangling, so do I understand correctly when you're thinking about the fermions, there are kind of two steps? First you start with the bilayer to make a low entropy gap to diamond lattice, and then you can maybe adiabatic or transform this to the final desired gapless state?
Exactly.
Okay, and so the first step, you made this awesome point that you only need sort of local transport, but in the last step, does it actually require longer scale, longer time scales for correlation relative?
So in this sort of sense, you still have the same conclusion in terms of mass transport. It's kind of clear that that at some point here you're relying essentially on a finite size gap, or alternatively, there's a time scale for the correlations to spread through the entire system, and if you go too fast, then you get essentially a shorter correlation length. So absolutely, the bigger the system, the slower the process has to be. What's kind of nice is that when you don't have long-scale mass transport, in most of these cases when you actually do the calculation, the time scales over which you need to ramp to get very, very high fidelities are surprisingly short. So again, these things are in units of the tunneling time scale on the stronger bonds. So again, we're looking at a time scale of the order of sort of tens to sort of 100 tunneling times sort of for time scales of typical experiments. So from that point of view, we're
kind of a related question. If you're in a regime in a Fermi gas where you have essentially no charge entropy, but spin entropy, is there a difference in time scale in that regime when you're essentially below the superexchange scale?
So in the end, it sort of it depends on the exact setup. So if you have for example just a spin gap but not a charge gap, then in that particular case, I'm not sure sort of exactly how I would go about the sort of protocol. Normally what we have here is a charge gap and a spin gap, which actually sort of gives us additional opportunities to redistribute the entropy.
There's no difference between having a system which is a perfect mine insulator, so you have no charge gap, or you have no charge entropy, but a gap. And then the only entropy remaining is the spin entropy.
Right. So that, and the thing is that if you don't have a spin gap, then it's hard to actually then you can't use this sort of process without a spin gap in order to bring the entropy of one layer sort of down below that superexchange energy. So what you need to do is either sort of introduce a gap by having this sort of this dimerized lattice. That's sort of what we're doing, sort of introducing the gap in that way. Or if you have spin-dependent lattices, you could induce a spin gap that would allow you to do this type of process by having different tunneling strengths for the two different species. So either way, you could then apply this.
Time for another question. Yeah.
So in cold atoms, the most powerful tool, of course, is evaporative cooling, right? So I was wondering, are there any thoughts to do something like evaporative cooling for spin systems? Where you basically evaporate a, let's say, a marker or spinon, whatever excitation you have.
So I think it's an interesting question. And again, I mean, you could think about the type of thing that we're doing here as a kind of evaporative cooling, because what we're doing is we're putting the entropy in one part of the system and then basically cutting it off. So in principle, you could do the same sort of thing if there are ways of taking sort of magnons or spin-ons and kind of creating some sort of change in the potential for them that force them to a particular part of the system. I haven't thought specifically about how to do that, but I think it would be an interesting thing to.
Okay, last question, Christian.
And that is, of course, limited by the entropy capacity of the second layer. It's not, and of course you were emphasizing it's nice surface, but that comes at a cost that your system and your reservoir is the same size in some sense. Each is one layer, roughly same atom number. So I was wondering, what is the, I mean, okay, I could read that off the graph. What is the factor you gain maybe optimally, and how would that scale? I mean, in principle you could scale that up to put more layers, which of course we have, well, some problems of doing that.
Okay. So yeah, so you could in principle try to scale this up by adding more layers, and I think that would be interesting to do. I should emphasize when you ask for optimal numbers that we haven't actually specifically optimized this time-dependent ramp. And so just guessing at what might be good, we got factors of 10 starting with sort of low entropy per particle. We got factors of sort of 2 or 3 starting at higher entropy per particle. If you applied optimal control techniques to this, you could probably do much better than what we have with the ramps that we've guessed.
All right, let's thank Andrew again.